Okay, here we go. Cosmic coincidences, and now I want to tell you how they relate to the IHX relation. So, but let me remind you where we were. So we want a universal finite type invariant, so a map Z from the space of knots to the space of core diagrams, which again are, the space of diagram modulo antisymmetry and IH. So this is equal to diagrams modulo antisymmetry, sorry, this is not a problem with the whiteboard, it's a problem with my coordination. So antisymmetry, IHX, and STU, and we have a construction. The proof that it works, I will not show. It's actually not beyond the scope of this class, but it's too lengthy and I want to talk about other things. But I want to give you the spirit. I want to give you what's the main point. I mean, I think our discussion is incomplete if I don't tell you how the relations enter. So I have to get there. Anyway, the construction was as follows. For every diagram D, in the space of allowed diagrams, so this belongs to the space calligraphic D. So for every such diagram, we define an integer valued invariant, not quite invariant, number, quantity, which is associated with that diagram, a knot, and a choice of stars in heavens, okay? And the quantity is the number of ways you can place this diagram constructed out of chopsticks on top of the knot in such a way that all the chopsticks are pointing directly at stars. And last time we computed that this is the same as solving a system of equations or finding the inverse images of a point under, or finitely, or a number of points under a map between spaces of the same dimensions, and this usually comes with signs, and so you count with signs, okay? And then you make a generating function out of this. So you define z of k, this is the z that we're looking for, to be the sum, so ignore the normalization things, and ignore even the last normalization, though I will talk about it later. So it's just the generating function of all such cosmic coincidences. So you sum over all diagrams, the number of cosmic coincidences for that diagram times that diagram. So it's a formal linear combinations of diagrams in which the coefficient of each diagram, so meaning that it lives in this calligraphic A space, meaning that the coefficient of each diagram is the number of cosmic coincidences for that diagram. Now, I don't want to argue that this is an invariant as stated. I want to argue that it's an invariant, it's an invariant only after you mod out by the relations. And I want to explain why this is so. And I'm having a bad technology day. The scrolling is slow, everything is slow. Yes?
Yeah, before that, a quick question. So, is there correspondence between the chopstick and the axe of the knot? Or you can place any number of chopsticks on a particular
Sorry,
arc?
is there a correspondence between the chopstick and the crossings of the knot?
No, I mean the arcs.
The arcs? No, not at all. So, you could have even on a relative, how did we skip so far back? Okay, even on a relatively simple knot such as this one, you could construct a chopstick configuration with 2 trillion chopsticks. So you could construct you know, a chopstick configuration where you have, I don't know, the internal diagram could be like this, okay? You could construct, or you know, maybe you could even have, the diagrams don't need to be planar, right? So I mean, basically you could make an arbitrarily complicated diagram. So in fact, the space A that we're talking about is the completed space. This could be an infinite, this is generally an infinite sum. Okay? Good. Right, so let's look at a particular situation and try to understand what goes on in it, and you'll see where things are going, okay? So let me just explain this picture. Okay, first of all, the cast, the people, the things on the right, so these are all many people who contributed in one way or another to this construction. So starting from, you know, the people who built Stonehenge, through Gauss, Witten, Vasiliev, Gusarov, Kontsievich, Raoul Bott, Clifton, and so on, and Dylan Thurston that was mentioned before. And now let's start to understand the picture. So here is a picture of a knot. Okay? So the knot is in dark black here. So, you know, no, that's not the one I wanted to use. This. So the knot is this. Right? I'm now tracing it. Okay? Now, since the whole discussion, it's actually the knottedness is mostly irrelevant for the discussion. So then I kind of just indicated that it looks like a knot by putting a knot bit here, but the rest I just drew as an arbitrary curve in the plane. Okay? Furthermore, let's assume for the picture, just for the purpose of understanding what's going on here, that everything is in the plane. Let's also assume that there are 5 stars already specified in heavens. The orange star, which is far, far that way. The green star, which is far, far that way. The blue star, far, far that way. The purple star, far, far that way. And a red star. And the red star is your eye. Okay, so, sorry, not your eye, the eye of the video camera. So, you know, I am now looking from the perspective of the red star. Okay? Now, the orange star is roughly in the plane of my screen. Okay? The other stars, green, so green, blue, and purple are a little bit above the plane of the screen. So, you know, purple is in that direction, but not on the plane, but a bit here. Oh, you can't see me. Sorry. So it's not here, it's a bit above. Okay, here. Can you see me? Well, just above the plane, okay? I mean, same for green and same for blue. So, if I, so now suppose I'm looking for a cosmic configuration as indicated here. So, namely, I'm looking to find a way of placing chopsticks, a purple chopstick that will be on the curve of the knot, a blue chopstick that will be on the curve of the knot, a green chopstick on the curve of the knot, whose other ends are in a point on R3, and so that they are pointing the purple on the purple star, the green on the green star, and the blue on the blue star. Okay? So, I have to pick a beginning point for the green chopstick, right? The green chopstick should start on the knot, so I have to pick a beginning point for the green chopstick, and here is a potential interval where green could begin. So as I move green, as I move along this interval, seeing that green always points in the green direction, it creates a little bit of it creates a plane. Now this isn't really a plane, it's a surface, right? But it's the surface that is spanned by moving a chopstick, which always points in the same direction, along a line. And I now realize that I made a mistake, because I actually want the green star not to be above the plane, but behind the plane. And in fact, the same for the same for blue and for purple. So all of these should be in the next apartment, behind us a little bit. Okay? Now, so I have this green plane, and similarly I have a blue plane, which is constructed by moving a chopstick along the arc of the knot, where the chopstick is always pointing in the same direction, and I'm calling it a plane, but it's really a surface, but it sort of locally looks like a plane, right? That's what sort of surfaces are, okay? And similarly, there is the orange plane. Now, these three planes are tilted a bit in, right? Because the chopsticks are pointing a bit down. So they're all tilted a bit in, so it looks like a cup or something made out of three planes. Do you see the picture? Like a tetrahedron, like I don't know, you have one of these things in the Louvre in Paris. Anyway, so if you have three planes generically, they meet in a point, the point in the center called O here. You see it, right? Okay? So that point here in the center corresponds to a configuration that will be counted with this diagram. Now, what happens if I move the planes a little bit? Or sorry, if I move the data a little bit. So what happens if I move the knot a little bit, if I deform this line a little? How did it change to something else? I'm sorry. Right, what happens if I deform this line a little bit? Instead of being the black line shown, I deform it a bit. Or if I take the green star, which is here somewhere far, and move it a little up or a little down or a little to the left or a little to the right. So long as it is little, these planes move a little bit, but the intersection point of three planes is a stable thing. If you move the planes a little bit, where you had one intersection, you would still have one intersection. So the count does not change. Okay? But here is a slightly more complicated situation in which the count will change. So for this, I need two more stars. The orange star. So the orange star, I'm looking for chopsticks that start around here and that point towards the orange star. And I remind you that the orange star is, you know what, maybe it's also a little bit behind the screen. So I get the orange plane pointing to the orange star. and the orange plane intersects the valley created by purple, blue, and green. And you know, if it starts behind and intersects this way, you sort of see an orange triangle which is not hidden by these planes. Okay, do you see the picture? So, in fact, what are the vertices that are now created? So, for example, what is this vertex? This vertex here will correspond to a contribution. So, in fact, why don't I now mark it in more permanent ways? So, this vertex will correspond to a contribution in which you have an orange chopstick, a purple chopstick, and a blue chopstick meeting. So, I don't know, let's substitute orange for red, and purple I have, and blue. So, these correspond to the same diagram but with different colors. Okay? Similarly, for this one, and similarly for this one. Now let's add another picture. Sorry, now let's add another star. And the other star will be our eye, or your eye, because you're looking at it from the direction of the video camera. So now new new planes are created, new potential intersections, and it's very, very complicated. But let's look, for example, at the point I. The point I, I didn't know I could edit images this way. Anyway, sorry. The point I is defined as follows. So you look at the line of intersection between purple and blue. So this is this black line here. And it continues even beyond the intersection point. Okay? And you look at the line here, which is the intersection line of orange and green, of orange and green, and these two lines at some point will cross, right? So this line at some point crosses that line, and the point I is the point in which these two lines intersect, in which these two lines cross when they are projected to the plane. But three-dimensionally, these two lines don't meet, right? The blue-purple line is behind the orange-green line. However, you could connect these two lines by a vertical chopstick. Vertical means pointing at your eye. So in fact, you only see it as a dot. And this dot is this red dot corresponding to this cold eye. Now, what is the configuration corresponding to that I've just described? So, the configuration corresponding to having a vertical chopstick here called eye. So, in this configuration, you have a green chopstick pointing to a point in R3, an orange chopstick pointing to the same point. So this is a green chopstick and an orange chopstick, both pointing to the same point in R3. And then you have a vertical red chopstick. This is this red chopstick, and it is pointing to a point which is in the intersection of the orange of the purple plane and the blue plane. So so the other end of this vertical red chopstick it starts at a point at R3 in which a blue chopstick meets a purple chopstick. So that's exactly this configuration. So the point I corresponds to a contribution to the diagram shown here, which is the diagram I. Okay? Similarly, the point H corresponds to a contribution to the diagram H, and the point X corresponds to a contribution to the diagram X. Now, okay, sorry, the setup is really complicated. I'm aware of that. It's a complicated description. Yes, Leonard?
So, yeah, I don't get where the stats. So, are the stats behind in the other room of so behind the screen? I mean the stars.
The start?
The stars.
The stars, yeah, the stars are behind. So like these planes are tilted inwards. Like the three main planes, the purple, the blue, and the green planes are tilted in. Okay, so I wish I had, or I wish I had thought of it in advance, but I don't have basically, so it looks like a cup. Okay, like
a cone, right?
A cone, a pyramid, an inverted pyramid. Okay, so a pyramid whose tip, the point O, is not above the plane but behind the plane. And then orange cuts through this pyramid, so it's as if the pyramid was a valley, and you fill it in with orange juice. So you see an orange plane. Okay? Anyway, so now let's move the picture. If I move the picture just a little bit, still nothing happens. So if I move this curve, and at the same time move the orange curves, then all of these planes will move a little bit, and all of the intersection lines will move a little bit, and so the 3 points will move a little bit, and nothing will change to the count of the coefficients of IH and X. But then occasionally a catastrophe will happen. What is a catastrophe? A catastrophe is when the combinatorics changes. So for example, if in all this motion of planes and lines, and intersection points of triples of planes and so on, if a plane passes across an intersection point of 3 other planes. So for example, if the orange star, the orange star is somewhere here, if you push it down, which is equivalent to, if you push it down, the orange plane goes down, 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 so it's as if you drained a puddle of orange juice. You drain it, and suddenly it disappears, and then you push it even more down, and in fact it doesn't really disappear, it just reappears inverted on the other side. It just becomes, right, because all of these planes continue, so it just reappears inverted on the other side. Okay? So what happens when you go through the catastrophe? So when you go through the catastrophe, everything remains the same, except basically the line, so for example, for the diagram I, the orange, sorry, something strange happened. What? I'm touching here, and I have, sorry, my technology is very misbehaved today. Sorry. Is it better now? No. What will happen if I start drawing? Oh no. Sorry, something very odd is happening today. Maybe no. Oh, good. At least things are in place. Good. Sorry. So again. So if the orange plane goes to the other side, the intersection, the line of intersection of blue and orange is still there. Sorry, blue and purple is still there. Also, the line of intersection of orange and green are still there, except that instead of the lines being organized in R3 like this, they swap order. Which really means that the red chopstick that runs in between them, it's actually my straw, right? The red chopstick that I don't know if the picture is good enough. Anyway, the red chopsticks that run in between them changes orientation from going up to going down, or depending on your conventions. I mean, it swaps, it changes orientation. This amounts to saying that the contribution to this diagram changes by 2. Okay, from +1 it goes to -1, or maybe from -1 it goes to +1. But at the exact same time, the time in which the orange juice puddle gets completely drained, so at the exact same time, the contribution of this diagram changes by 2, and the contribution to this diagram changes by 2. So, if you mod out by the sum of these 3 diagrams with appropriate signs, nothing changes. And that's the IHX relation. That's where the IHX relation comes from. I don't know, I hope you could follow. It's a complicated picture, but it actually explains where the IHX relation comes from. Anyway, the next thing to do, again, I'm sorry, I'll have to debug, I'll have to understand what exactly went wrong today with the technology. But anyway, there are several other catastrophes that may occur, and you have to enumerate what are all of them. Okay? And I'm terribly sorry about the slowness of all of this. But anyway, so here is one catastrophe. A plane like the orange plane for us crosses over an intersection point of 3 other planes, and the way you resolve this catastrophe is you impose the IHX relation. If you impose the IHX relation, the sum doesn't change. Now it's going to scroll too far. Okay, now let's scroll back, but hope that I don't scroll back too much. Okay, there is another potential catastrophe is if an intersection line between 2 planes, so say the intersection line of the green and the blue plane crosses through the knot during some motion, crosses through some other place on the knot itself. It turns out that the change to z is proportional to an STU relation. And then the last interesting catastrophe is kind of funny. So every 3-dimensional curve has what is called its Gauss curve. the Gauss curve of a three-dimensional curve. So really this is a map from curves in R3 to, so this is the Gauss curve map, to curves in heavens, namely in S2. And the map is very, very simple. You pick a laser pointer. Fortunately, I have one. Here you go. Does it show? Well, it will show if I point here. Okay, so you take a laser pointer, and you slide it along the knot. You basically slide it along the tangent of the knot, and then it always points at a point in heavens. Heavens, as you know, is just a big sphere out there, so the light from the laser pointer gets reflected, and then that dot that moves in heavens is the Gauss curve. Now, when you deform the knot, or when you move the stars, we also have the stars in heavens. Okay, maybe I should say, generically, you have finitely many stars in heavens, and the Gauss curves misses them, because a random curve is not going to meet a random collection of points for dimensional reasons. But if you start deforming this curve, so if you deform the knot or move the stars around, then there will be the occasional times in which the Gauss curve will cross over one of the stars. Okay? And it turns out that this is a catastrophe of a different nature, and I will not go into it, but it's more similar, it's more like a Reidemeister, it's similar to the Reidemeister 1 issue. In fact, think about it this way. What is a Reidemeister 1 move? A Reidemeister 1 move, or what happens from the perspective of the Gauss curve when you do a Reidemeister 1 move. So when you do a Reidemeister 1 move, well, the Gauss curve, right, if I kind of move around the laser pointer, on the left is, so the Gauss curve corresponding to the curve on the left is equatorial, is near the equator of heavens. But then at some point in the middle, between these two sides, at some point in the middle, the curve would look like this. It will kind of get to a point, move vertically down, and then twist and come out. At that point, the Gauss curve points either straight down or straight up, depending in which direction you go. You know, maybe I'll try to show it with an actual curve. So, you know, here is a Reidemeister 1 move. If I here is the kink before the Reidemeister 1 move. It's not rigid enough. Yeah, I don't see the right object here. If I try to pull it straight, at some point, like here, the Gauss curve will be vertical. So in fact, a Reidemeister 1 move is a situation in which the Gauss curve passes through your eye. Right? Passes through the star which is your eye. So a similar catastrophe, okay, and these the correction to these, to Reidemeister 1 issues, like in the Jones polynomial, is to multiply by some counter term. And there is a similar counter term that can be multiplied here to fix this issue, this catastrophe. And again, I am not showing it, it's beyond our scope, and but that's it, that's the end of the sketch. I hope you didn't suffer too much. That was supposed to be storytelling, not really rigorous mathematics. But there is rigorous mathematics behind it. Maybe I'll say a few more words, okay? So first of all, the more standard presentation for the same thing is in terms of integrals. Rather than in terms of counting, it's in terms of integrals. So maybe you know that, you know what, let me use the space that I didn't use above. And let's just hope I will get there without too many catastrophes. So, okay, now I have to wait for it to stop scrolling and hope it will stop scrolling at the right place. I'll fix it by next time. Okay, so, you know, maybe you know that, for example, if you want to count the number of times a curve winds around or winds around a point, right, the so-called winding number. So one way to do it is to pick a direction and count how many times it crosses that direction with signs. Another way to do it is to pick a direction in heavens. Now we're in the plane, so heavens is just a circle. So you basically choose a circle around this whole picture and you pick a direction in that circle, and then you look for times when the tangent to the curve points in that direction, and then you count these times. And another way to do it, so another way to define the winding number of a curve gamma, so this blue thing here is the curve gamma. Another way to do it, and let's say this is the point 0, is to use something like the Cauchy integral. So it's the integral along gamma of dz over z, and probably you have to divide by 1 over 2 pi I or something like that. Okay? So there is an integral form for counting things. And in fact, more generally, if you have a map between two manifolds of the same dimension, so phi goes from m to n, and both of them are of the same dimension, and let's say both of them are compact and oriented, and you pick a point in this manifold, and you want to count its inverse images. This is very similar to what we've been doing. So you want to count the inverse images of that point. This is the so-called, sorry, not with absolute value, just count them, but count them with signs. So there is some local orientation and you can count them with signs. So this is the so-called, degree of the map phi. And the degree of the map phi can also be computed as follows. You choose a volume form omega, so a top degree form on this manifold, whose overall integral is 1, so that the overall integral of omega on n is equal to 1, and then you compute the integral over m of the pullback via phi of omega. And that is the same degree. So basically, computations of coincidences, this is computing coincidences, can be done using integration. So the same thing can be done for us. So oh no, okay. I'm afraid, I want more space, but I'm afraid of creating it and getting a mess. So I'll try to write everything in a very small space. So, for example, the pairing, like the Stonehenge pairing between this diagram and a knot, so this is the Stonehenge pairing. So, is really, you construct a map phi from the way of placing, so basically the ways of placing all of these points, so S1 cross S1 cross S1 cross R3 into S2 cross S2 cross S2. These are the directions of the three chopsticks. And then you pick a random point here and compute the number of pre-images. So instead of doing this, you can pick a volume form here. So really you pick a volume form on each of the sphere and multiply them. So you look at omega tensor omega tensor omega, where omega is the ordinary volume form of the sphere, and then you compute the integral over this manifold, let's call it M, the integral over M of phi star of this omega wedge, omega. And something similar to this you do for each diagram. Now I am telling you lies, because the degree theorem is true for manifolds without boundary, and here there are all sorts of boundaries. The points are not allowed to meet each other, or else the lines between the directions of lines between them will not make sense. The points have to retain their order. So when I write S1 cross S1 cross S1, it's really up to, it's really a subset of that, because I want the point to retain their cyclic ordering. So the manifolds here are manifolds with boundary. Okay? So it's not quite the same degree theorem, but you end up having a similar formula. So the same Z can be constructed using integration. And that's the typical way in which it is presented. It becomes some very, very complicated sum of integrals over configuration spaces of points. So basically it becomes a very complicated integral over configuration spaces of many points on the knots, and and possibly more points in R3. So it's a very high dimensional integral. And then the proof of invariance is really presented usually not using the geometry that I've given, but using some sort of very, very clever application of Stokes' theorem. But the last thing I wanted to say is that this is also related to quantum field theory. Do I have time to say that? So, maybe I'll ask you. So, you know what? No, I think I want to close. Well, you know what? Maybe I'll ask you. the very, very vague relation with quantum field theory is as follows. So in quantum field theory, one wants to compute certain infinite dimensional integrals. So this integral here, the outer integral, is an integral over an infinite dimensional space. It's an integral over the space of all Lie algebra valued 1 forms. So it's some huge infinite dimensional space, and one wants to compute the integral over such infinite dimensional spaces of the exponential of a Lagrangian, where the Lagrangian is something quadratic plus a perturbation which could be higher than quadratic. And then, so this particular Lagrangian was written by Witten, but the technique for how to compute such integrals, or one technique for how to compute such integrals, so for mathematicians these integrals don't even make sense because there's no Lebesgue measure on an infinite dimensional space. Yet Feynman wrote a collection of techniques for how to compute such integrals, and basically the result is that this integral is equal to some big series. M goes from 0 to infinity of another sum of Feynman, so-called Feynman diagrams named after Feynman, but you've probably seen them at least culturally, if not rigorously. And for each Feynman diagram, you have to compute a super multi-integral, complicated integral over some high dimensional space. So let me write it as r to the power n, where n depends on the diagram, but it's not really r, it's a manifold. And here you have some very complicated integrand. This is schematically what Feynman found. But the point is that, I mean, this was infinite and impossible to compute, and this is maybe still very difficult, but at least it's finite dimensional. When you do the Feynman procedure to the Witten-Chern-Simons Lagrangian, the result is the diagrams becomes the diagrams we were talking about, the integrals becomes the integrals that I mentioned. I'm pointing up, right? The integrals that are up above, I could scroll and show them, but then we would lose half an hour. I've given classes before. If you want to look back at the class I gave, I think in 2014, so I gave a full semester course on basically doing this. So it can't be done very, very quickly, but I can at least give you the flavor. So I can give you another hour, which would be as vague as this one, but in which at least it would start making sense how computations like that becomes diagrams whose ingredients are integrals in a finite dimensions as opposed to infinite dimensions. This should fit in an hour. So the options are either to do that or to move to a new topic, or move on, but regard this particular topic as if it's done. So what do you say? Should I spend more time on Feynman diagrams, or, and again, it will be very, very vague, but there will be information in it, or should I just move on? Okay, so let me turn off the video, but class is not